good to see you guys too. And what an amazing presentation list that we've had here this morning talking about the future. I think it's been a very long time since I've been this excited about Wi-Fi. I was just getting news from my guys in the lab too that was kind of perking my ears up. It seems like every day we're doing something amazing around here.
Totally.
Well, Jim, we are extremely excited about having you here and about Wi-Fi every day. So first thing we do when we wake up is we think about Wi-Fi, and then we think about having you on our Wi-Fi day. So let's crack on with the presentation. I'm sure that everyone is dying to see what you have to say.
Good. I think it supports pretty much everything we've been talking about here today. You know, as everybody knows, unless you've been living under a rock, and certainly this crowd has not, Wi-Fi 6E, the planning challenge. I don't know if everybody's life is like mine, but the second engineering starts to develop a new technology, the very first question that comes back to me is, how does this change design? How do people design differently? Well, 6E actually did make a significant change in how we define a design in a lot of good ways. And like every technology that we've broken into with Wi-Fi, the really good news precedes it, you know, plenty of bandwidth. And then you start to hear, you know, the caveats that go with that and the concerns about, you know, whether or not we're going to be able to support this realistically. What does that mean to my existing infrastructure? People are very loath to move APs these days. I can tell you that's one argument we take back all the time when somebody says we're thinking about changing our bracket. It's like, please don't. So the challenges up front were, you know, Wi-Fi planners. We didn't really have any, not initially anyway. For 6 gigahertz. Ekahau AI Pro, thank you very much. That has changed the game, and it's actually helped us a lot to demonstrate, you know, what we've been thinking about Wi-Fi. Wi-Fi measurements, being able to measure things at 6 gigahertz, and thank you Ekahau Sidekick 2, which I am desperately anxious to go test and would have been running with this week, finally after the travel I've been doing. Except for a small mishap at the beginning of the week, we'd have actually had some thoughts on that. So the question that comes up most often is 5 gigahertz. Can we use it? How's that going to compare to 6 gigahertz? And I think the data that you presented at the very beginning of this sums it up. People do want to do that. They want to keep their APs in the same place. They don't want to go pulling new cable. Not only is it expensive, some environments are 24 hours a day and health and safety related and just don't have the luxury of relocating all their APs, or it's not within their budgetary reach. You know, you add to that the things that we're doing now with the bandwidths that we're able to achieve and the speeds that we're achieving and the demands that we're putting on it. And you've got a lot of other things going on in your infrastructure, looking at power on the switches and realizing that as we keep strapping radios on, we get more efficient, but things go up. You need things just besides the radios being on. So we did some testing. A lot of this data, we have kind of been around it this summer, looking at it. We're going back and we're adding more data to it. But the things that actually have caused some concern. And you can go ahead and change the slide there. There you go. Things that have caused concern are the normal ones. I remember when we drove into 5 gig, and 5 gig was a fair jump in frequency and had very different properties. This time we're just going to 6 gig. So you hear, you know, path loss is not going to go as far as 5 gig. Cell sizes are going to be smaller. Absorption reflection properties are going to change through materials. And all of this is true. It is not to a degree that I think is unmanageable. And meanwhile, there's a lot of talk about AFC going on. I actually heard that, you know, low power indoors was going to be kind of useless. And I couldn't get my head wrapped around that. But if you're assuming LPI and the same power with 5 gigahertz, that's going to be uneven. But the good thing about Wi-Fi 6E is it is not Wi-Fi 6. It's Wi-Fi 6 in a new spectrum with new rules. Go ahead, advance the slide. So this is a time-worn one. and around the world, and the advances that have been making, we're still hearing advances being made on a almost a daily basis. You hear something else coming out of the standards committee. It's like watching the stock market. It goes up, it goes down. You have to look at the longer term to really make sense of it. But folks that have initially ratified 500 megahertz are already looking at 1200 megahertz. So this is something we're tracking as well. And I think most manufacturers, certainly Cisco's making plans. 6 gigahertz is coming to a network near you, I promise. Go ahead, slide. So one of the things that came with this that made it really difficult as a Wi-Fi designer or somebody who's got experience with Wi-Fi and figures you can get your arms around this is the power levels were all different. We represented them differently. And if you take a look across the world at the limits and what they're doing, I mean, this reads like, the Tower of Babel. And then that's just the LPI portion of what we know right now. And then the SP standard power portion, which fortunately or unfortunately, however you look at this, US is the only one to deploy that right now, working to deploy that. And that's going to require some automatic frequency coordination. So all of these power limits and everything, these come out of a not unrealistic concern that Wi-Fi is going to interfere with incumbents or several people that have been using these frequency ranges. And the maximum amount of caution has been put on this. Of course, Wi-Fi has to accept and must react to all interference by getting out of its way. But much of the concern in the community and a lot of the pushback was from these incumbent operators who have a very real investment in these frequencies and radio technologies. So it was by design built much like we did in 2.4 and 5 gigahertz. These are not new concerns. Somebody's always occupying a spectrum before Wi-Fi gets it. The amazing thing is that we did get it. So making sense of this, making sense of all these rules and the max power PSD and the US, of course, we have, a 6 dB offset from the max power of the AP. It makes one's head swim a little bit. Slide. So we kind of focused in on just looking at some of the ones that have some pretty wide differences, but kind of breaking this down, not for the differences, but for the sameness of it. Taking a look at just the FCC region, ETSI, and the UK. Go ahead, give me a slide. So when we first saw the PSD limits that Europe got and that the UK got, and I remember my reaction immediately was like, man, doggone, I wish we had that, right? But you've got to look at the two components here. There's a max EIRP at any point, right? So when you break that down, it really does make sense, as was stated earlier, and I think most of us have come to accept. If you're working with 500 megahertz of the 6 gigahertz spectrum, it probably makes the most sense to operate at 40 megahertz channels so you don't exhaust your channel space. But if you're in FCC with all of that massive amount of spectrum, 80 megahertz makes the most sense. And when you take a look at the power levels at 80 megahertz, and you realize that these other PSDs are great, but you still can't go over the maximum limit. What we've got, and if you go back and look at this in other regulatories, what we've got largely around the world is a pretty level playing field. In fact, other than the number of channels, the power levels are a little more level than they've ever been for Wi-Fi, which is a really good thing. I know that there was a couple of teams, and I live in Maryland, so I'm very close to Washington, D.C. The government affairs office for Cisco is folks that I deal with on a regular basis. So I know that was one of the goals, was to try and make Wi-Fi more homogeneous, easier to deploy in sameness around the world. Give me a slide. So looking at the channel space, I actually put this together. Channel exhaustion has been stated is one of the primary things that we look at when we're designing, particularly for capacity. Most APs out there now have more than one radio operating, sometimes 2 in 1 band. Those consume channels, and that channel overconsumption of channels is probably one of the problems I deal with on a daily basis. And usually from well-meaning folks who have just, they've gotten tired of trying to support 2.4. They've got 5 gigahertz. They want it all to be 5 gigahertz, and they exhaust their channels, which of course leads to interference and is entirely why Ekahau exists and why we absolutely wonderfully support a design effort, because you can get really good results if you plan on it. So comparison of the numbers of channels around the world, we're pretty good at 40 megahertz, with 12 channels, which compares nicely with 5 gigahertz right now. I get 14 at 80 megahertz, which is really a nice surprise, and increases that channel reuse rate or reduces it. Next slide. So the question is, can I replace 5 gigahertz AP placement with a 6 gigahertz AP? And as been discussed, we're dealing with two different bands, two different limitations. There's concerns about roaming between the bands. There's a lot of detail that we're fleshing out now in client discovery and everything else. But if I take a look at what an enterprise, a carpeted enterprise, and this relates directly to that model, because there are caveats, we're looking at an average of about 1,200 to 2,000 square foot, 110 to 185 square meters on average for cell placements, and the distances between those cells. So the question was, in these environments, what are the power levels they're using at 5 gigahertz, and how does that compare to 6 gigahertz? Slide. So we went back. Being Cisco, we've got a fairly decent sized database from customer implementations, anonymized, of course, cloud implementations that we've got running now. And we've got visibility into what power levels these APs are running. And what we found was the most common areas, if you're looking in these carpeted environments, are operating somewhere between 11 and 15 dBm transmit power. And that makes perfect sense. That's what my gut level said that we were going to find when we looked at that. And we actually backed it up with some TAC data. There was some outliers in there, but we're not able to break it out directly by use case or how I would have liked to kind of exclude warehouses. It's whole customers. So you've got some mix of the deployment in there. What we see on a daily basis, though, is power levels 3 to 4. Slide. So we decided to test this two ways. First, we were going to take a look at the propagation. And to do that, when we did this testing, which was back end of May, very early June, we used client devices to actually measure record the RSSI and their experience 12 different test points across our offices in Ohio, which is an active office. So it's laid out just about like everybody else's right now, with some open spaces, some closed offices around the side. And then looking at that, comparing 5 and 6 gigahertz measurements using a reference AP, and then seeing what the impact was with the construction in the office or changes in terrain, open versus cubed environment, and get that comparison. The second way we wanted to test this, because coverage is one thing, signal to noise ratio is going to be an entirely different thing. So the second way we wanted to test this, assuming that the client can never make more than about 6 dB of the max power of the AP, is that a factor? So we actually did some range versus rate testing, doing both uplink and downlink TCP throughput testing to kind of validate whether or not our assumptions around a cell are valid, and whether we can actually see that kind of throughput, and whether it impacts us at distance, or how much that change is. Next slide. So the propagation test, we laid out 12 test points. We used 5 clients. We had a Lenovo laptop, 2 Samsung laptops, 2 different Samsung laptops. I think it was a Book and a Galaxy laptop, and an MSI laptop, and a Samsung S21 phone. And I want to echo what you said earlier, Matt and Mac, was that there are clients out there that, and you will see it, it's 10 or 11 dB. It's a very dramatic drop in the RSSI that you're experiencing at 6 gigahertz compared to other clients when they use a 5 gigahertz antenna. or if that stayed in their plan when they put a 6E chip in there. So you do have to be careful of that. Characterize your clients, absolutely. But we did record and measurements, and then we compared the 5 gigahertz measurements against Ekahau site survey using Ekahau Pro and the Sidekick 1. What we wanted to do was get an idea on the planning, how that compared with our actual measurements. Go ahead, flip the slide. So across our environment, we went out to about 70 feet away from the test AP. And keeping in mind that this is an active office, we did take note of what was deployed already, and I had to walk past 2 APs to get out to 70 feet, but we wanted to give this a really fair test. And there's mixed environments. Right down there in the lower corner was full-size cubes with open areas and closed-in offices across the top at 5, 6, 7, and 8 test points across the top. We did this and we compared at 5 gigahertz at Cisco power level 3, which is 15 dBm. We measured that channel 36 at 40 megahertz. And then we set up the 6 gigahertz for power level 1, which is 17 dBm out to the antenna. And we did that on channel 5 at 80 megahertz. Go ahead, next slide. We broke this, back up. Broke this down into zones, and what we found was the average RSSI, which is the way we calculated this up, and you've already seen a peek of that. The data is all on the next page. But that average RSSI between 5 and 6 gigahertz kind of proved out that with a small offset in the power levels, you can actually even up the experience of those cells. Add to that there's less noise in 6 gigahertz, at least now. Less noise than 6 gigahertz. The experience actually isn't all that horrible. Next slide. So here's the data, the raw data, the top table being 5 gigahertz, the bottom table being 6 gigahertz. And that very top line in the top table is what we measured with the Ekahau Sidekick 1. We did visualize everything in the mobile device mode to make it as fair as we could. And in most cases, the results that I got back from that Sidekick were slightly less or right about even with what we were actually measuring on the client's RSSI, which is incredibly encouraging. I don't know how you folks do things, but I love conservative measurements. It gives me room to be wrong. And that is an important thing in Wi-Fi because a lot of things can make a liar out of you, especially as they change over time, as you all well know. So the data look good. I will say this on the clients too. I was a little concerned about doing this because we've been doing testing on 6 gigahertz clients almost as soon as they come out and not even fully released or even have drivers released for them yet. And I have seen a steady march of improvements in the RSSI that we're seeing out of the chipsets. And all of this is driver related work. And none of this is new. We've seen this with every new technology that comes out. It takes a while for everybody to get the experience with the new chipsets and write the drivers that you know best operate efficiently on that hardware. So we're not seeing anything different. This has been a long march, and it is a very new frequency range for us, which is different. Everything else that we've implemented, at least recently, has been across 5 gigahertz. But we saw the same thing. When 5 gigahertz was first released, there was a terrible problem with transmit power being available on a battery operated device. The oscillators just took more power. So next slide. The other thing that we thought about these coverage conclusions anyway was that, yeah, it does require more power to balance the coverage between 5 and 6 gigahertz. Okay. If the existing placements are somewhere between, 1,200 square feet or 2,000 square feet, average cell size is definitely within a range that you can accommodate that in power. The ceiling height, carpeted enterprise, it's possible to configure and do that. If you have high ceilings, you got open atriums, you've got any edge areas, probably the best thing to say here, and I was very reluctant to say you can go out and deploy 6 gigahertz and just rely on replacing one for one, because every installation has got an area where they're not that dense. So it's probably better to go out and do a survey first. understand how solid your 5 gigahertz is and look at the entire coverage model and capacity requirements fresh. It's always good to take a fresh look at things. Things that are going to matter: brick walls, elevators, things that are not sheetrock and glass, and even glass does matter. But in an open office environment, it's not horrible. And that was really the goal of this testing, was to see that it's not horrible, because I've been listening to a lot of things and wondering how the math stacks up. Ekahau Sidekick 5 gigahertz measurements displayed in mobile device mode were very adequate. I don't bother setting offsets for everything. There's too many devices out there, and we're usually configuring to a range of devices. And as we all know, building a Wi-Fi network is actually relatively simple. Getting clients to connect to it's a whole other story. Next slide, please. So that covered coverage. With those assumptions intact, what does the performance look like? When we look at the performance across that range at enterprise densities, same density, we're looking at nominally about 25 feet between APs, 7 meters max when you're talking about that density of cells. So we took the same 5 clients, all right, and we did a TCP throughput at 5 and 6 gigahertz. Actually, I think I have 4 of them displayed on the next page because of the constraints in formatting. But we tested them both at 5 and 6 gigahertz across the range. We used a Cisco Catalyst 9136 configured for 5 gigahertz, and we dropped the power this time. We dropped it down to power level 4, which put me at 11 dBm, which is also within that range. And we dropped back 6 gigahertz to 14 dBm. And we did this at 40 and 80 megahertz respectively. We did that to really simulate, to really challenge the performance from what we did with coverage and see if it made a difference. And then we gathered the data at 5, 10, 20, and 25 and 30 foot increments. That's for those of you logging in from the other 101 countries. 1.5, 3, 6, 7, 5, and 9 meters respectively from the AP. All of the devices were 2 spatial streams at both 5 and 6 gigahertz. Next slide. We were actually pleasantly surprised because I really expected to see a bigger delta between uplink and downlink data and across the range using TCP throughput measurements off of Chariot. Across the range of devices, while you saw some devices perform a little better than other devices, it was all fairly close. And the devices themselves, uplink and downlink, really performed very well in our testing. So that's the data. That's what we saw when we compared this. Next page. So that begs the question, where does that leave us on 5 and 6 gigahertz assumptions? And this is heavily caveated. And I in fact try not to say this internally too much, because most people hear your first bullet point and roll with it. In the caveats, look, if you're deliriously happy with your 5 gigahertz coverage, you know where it's at, you know where it's thin, you can do the easy plan. I would absolutely advise going out and taking a sample at 6 gigahertz. One of the things that does concern me, and I said this earlier, with the AFC, as well as all of the 6 gigahertz rules that have been written, they've been written so that we don't interfere with incumbents. I just spent last night pulling a lot of data for the Maryland area from the ULS database, and I'm getting ready to go out now that I got my handy dandy Sidekick 2, and I'm going to take some spectrum measurements, because there is not a thing in these regulations that say an incumbent won't interfere with you. And I believe that might become a factor in LPI. So it's good to have the tools that can tell you if these things are happening. Ultimately, can a 1-for-1 replacement of Wi-Fi 6 and 5 APs be achieved? It can. You need to know what you're doing. You need to understand the assumptions that you're making. And, again, like everything else, it's career tolerance. If you think you can get away with it and that's where they're going to push you, well, then you need to do that. But it is a much better practice, and will remain our recommendation, as well as others, that you go out and get some data, because better Wi-Fi happens by design. And I think that's all I had.
Jim, we cannot agree more with everything that you have just said. And design is indeed the core of everything that we do. I'm not sure about you guys, but I've learned a lot by listening to you. Amazing data, amazing session, great presentation. Thank you very much, Jim. Let's do it more often.
Best of luck to you for the rest of the day. I can't wait to hear what Ansi's coming up with next. In fact, I plan to get a cup of coffee and put my feet up and enjoy it.